briefly talk about quantum computing and how that would make sense, or how it makes sense to use quantum computers, and talk about quantum physics in companies. Maybe let me briefly start introducing the group I'm responsible for. So the group I'm responsible for is called Advanced Technologies, and it's very interesting. So what we do is look into technologies that could be strategically important for our company, that help us do things better, that make the lives of our customers easier. We have this group that's based on 3 pillars. So the first pillar is research. We of course do fundamental research, but mostly we look into how to apply things. One of these things is quantum computing, which we will talk about in a moment, and how we can apply it in the context of a company, so an industrial company, how it makes sense or not. That's the second pillar. So the first one is research, the second one is application. The third one is we foresee. So that's also something when the technology is not mature enough to be evaluated, to test it, we test it. We just have a look, but still want to be able to predict when it can be relevant for our company, when it makes sense to introduce it to our company and work with it. That's basically what we do. So we're not limited in scope. We look into things like quantum computing. We look into new forms of how to produce energy, like fusion. That's interesting for us. We look into optimizing traffic. We look into prediction of financial markets. So anything that you can imagine that could somehow make sense for our company or our customers. And now let's move over to quantum computing. So quantum physics in general, as you know, so it's always presented as a very difficult topic. It's a notion of complexity that physicists like Richard Feynman back in the 80s and before even contributed to by claiming things like, so anyone who says they understand quantum physics, they don't understand quantum physics. And I would go with a slightly different approach. I would say everyone can understand it. And it's not only all around us, it's in us. So everything that we see, everything that we sense, everything that is out there is, so quantum physics plays a role in that. And it all started about 13.8 billion years ago. So this is not a lesson in history, but it's just that I want to show you what I mean when I say it's all around us, or it makes us up. So about 13.8 billion years ago, when the universe started, everything was very small, compressed to a tiny point. So anytime we become really, really small, so about 10 to the negative 35 meters, that's called the Planck length, then all our ideas of classical space-time, everything that we perceive cease to exist. And the laws of quantum physics become relevant. So that's where the laws of quantum physics already were relevant at the very beginning. Then our universe expanded, and when we look at stars, some stars look red, some stars are in reality blue. So that's because there is a redshift. So stars emit blue light, and then it's stretched because the universe expands, because there is dust in between Earth and the star that we observe, and only the red light gets through. And all this happens because of quantum physics. And we ourselves, we live in a huge cluster. It's called a supercluster of galaxies, an agglomeration of galaxies. It's called Laniakea cluster with about 100,000 galaxies, and it spans about 520 million light years. So it's huge. And when you look at these stars, the motions of the stars are governed by classical physics, so we can easily calculate it. But again, anytime you become really small, when you look at the light that these stars emit, then it's quantum physics that becomes relevant. And if we go even further and bring that back to Earth, then we look at industrial applications. So where does quantum physics make sense and where we already use it? So there are lots of medical uses. So one is, for example, you have some quantum nanoparticles. And again, it's like this dust that I just talked about in interstellar space. You put that into people, and these particles, they attach to, let's say, cancer cells. And then you shine light on them, sort of X-ray radiation, and then you can make these cancer particles or cancer cells visible because the nanoparticles attach to these cells. Lasers wouldn't work without quantum physics. Material science is something where we go down to simulating molecules if we want to design a new chassis for a car, if we want to design a new battery material, battery chemistry, we have to simulate molecules on an atomic and molecular level. So parts on an atomic and molecular level. And that's also where quantum computing becomes relevant. It is, as some people say, the killer application for quantum computers, because you have one quantum system that will allow you to efficiently simulate another quantum system. We're not there yet, but still, that's something that's interesting. We have to look into secure communications, or not now, but maybe in 10, 15 years, we will have a challenge with current encryption algorithms, because it turns out that the ones that we use when you do telebanking, when you just log on to your browser and open a website, if you had a perfectly error-corrected quantum computer with sufficient number of quantum bits, then you would be able to crack it easily. So communication will not be secure anymore if we don't do anything. And that's also one of the areas that we look into. And now that's where we start to talk about quantum computing in industries. So we, as a group, we subdivided the areas of application into 4, which is machine learning. So part of artificial intelligence, you know, when you have algorithms that are trained to learn from data, you don't specifically program or write code in a program to do something. You provide an algorithm with data that can learn from data. So for example, you have the weather data over the last couple of days, and you always know what the weather was. Based on that data, you can make a prediction. So you say you have humidity, you have temperature, and some other attributes, and you feed that into the algorithm, and then the algorithm can learn, well, that specific day, or on the next day, it was nice and sunny, it was rainy, it was cloudy. And this is machine learning. So you provide these algorithms with data, and they're capable of learning. And how we can do that more efficiently, that's a thing that we look into with quantum computers. And there is optimization. When you think about problems like traffic is a very complex problem. You have vehicles moving in cities, and ideally you can access, so this is the research scenario, you can tell every vehicle how to move, and then you can avoid traffic jam. That's not what's happening in the real world. So you have access to a couple of vehicles. Some customers may opt in and say, I want to have a service that tells me the better route. And then I can maybe avoid traffic jam. So if you do that and you say you have a couple 100,000 vehicles, I'm sure in Vienna you have that situation, you have a couple 100,000 vehicles entering the city every day, then how can you let them move or regulate traffic such that the traffic jams are minimized? So the time that every vehicle takes from A to B, or wherever they want to go, is maximized. And this is a very complex problem. Imagine you have 3 routes per vehicle and you have 10,000 vehicles. Then the number of ways how you can distribute these vehicles is 3 to the power of 10,000. This is impossible to calculate with a classical computer. And anytime I say classical computer, I mean a computer that's not the quantum computer. So also classical computers work according to the laws of quantum physics, but they don't leverage quantum effects for computation. And so this is optimization, and only one example. I always have an easier time talking in examples. And then another area that we're very interested in is, as I said at the beginning, simulation, so molecule simulation. We try to take a molecule, and I imagine you have only a very small one. You have 2 atoms and you have some electrons around it. And anytime you add an electron, you have to simulate or calculate what happens with this electron and all the other electrons. It interacts with everything in that molecule. Now imagine you have thousands of electrons and you add one, then it becomes exponentially more complex. Again, something that you cannot do exactly with a classical computer. We all know, so especially I do because I work in IT, I know the caffeine molecule. The caffeine molecule, it is said to be, so it's not a super complex molecule, but it's said you cannot simulate that. So in a foreseeable future, and that means hundreds or even thousands of years, with the computer technology that we can envision classically. Classically is again not quantum computer. Maybe someone will come up with something that's not a classical computer and not a quantum computer, but for now we have quantum computers and classical computers. But with a quantum computer, if you only had 160 bits, quantum bits that are error corrected in that case, then you can simulate it. So that shows you the remarkable power of quantum computers. So a lot more efficient in some sense. And the last thing that we look into is IT security. And the IT security here, it's the encryption protocols that we're interested. We want to understand how we can make communication secure. So I work for a car company. Here it's very important that the communication between the vehicles is secure. We don't want anyone being able to hack that communication and take over a vehicle. That would be fatal. So this is something we have to look into. Even if it's far out there, very often you will hear in the context of quantum computing and IT security, it's not here yet. It takes 10 years. Yes, that's true. But you have to be sort of visionary in that scenario. So you have to have some foresight. We have to understand what's happening in 10 years because people own vehicles for tens of years sometimes. You can't just exchange hardware parts quickly. So we want to make sure that our cars are secure today. And how all this is possible, this is the last part of my brief talk today, is because quantum computers function according to the laws of quantum physics, as I said, but let's have a quick look to understand better what that means. So imagine when you have, in a classical computer science, the smallest information unit is a bit, right? It's 0 or 1, and it can be 0 or 1. When you look at it, it doesn't matter. And the string of bits, that's what bigger information is made up of. So more information, you just encode everything in bits, or the computer does. And anytime you do something on that string of bits, a computation, you can extract that result, the intermediate result, look at it, and it doesn't matter, no problem. But with a quantum computer, it's different. What you have is a superposition, that's what it's called. And if you have one bit, then this one bit can assume the states, the values 0 and 1 at the same time. So instead of being either 0 or 1, it is 0 and 1 at a time. As long as you don't look at it, and that's the crucial part. So imagine a bit is represented by electrons, and then you have an electron spin, and the spin can be spin up and spin down. That's my bit 1, that's my 0. And as long as I don't look at it, meaning firing laser light at it or photons, then it is in that superposition state. And what that means is, if I have 2 bits, which can take 2 values, is that they can take 2 to the power of 2 equals 4 possible states at once. With 3 is 2 to the power of 3 equals 8. So that means, in turn, if you formulate your problem right, all the solutions that a problem can have can exist at once, at the same time. And instead of querying all the solutions, let's say you have billions of solutions to a problem, like the traffic flow problem, you don't have to test every single solution and see which one is the best. You make one call to that solution pool, to that superposition, and if you do it right, you get the answer to your problem. And that only takes you a couple of nanoseconds, and with some additional processing time, maybe milliseconds, but that's it. So that's why you're a lot faster with quantum machines. There are some more effects like entanglement, so how you correlate bits and make one thing interact with another, like make that vehicle or take 100 vehicles here, move them over there. How do they interact with others? But classically, you can just say that's correlation. And another very interesting effect, and this is the last thing for today, is tunneling. So imagine when you work on an optimization problem, then you have, again, thousands, maybe billions of solutions to your problem. And you can imagine it as a landscape, like hills and valleys. And you can say the good solutions are in the valleys, and the bad solutions are on the hilltops. So what a classical algorithm can do, it can walk these hills and valleys. You can let it walk hours, days, whatever. And at some point, it will tell you, I'm in a deep valley, so this is the deepest I can find. You can parallelize, you can have 10,000 algorithms walk, or the one algorithm have 10,000 starting points and walk the surface. But at some point, it will tell you that's the minimum I can find. With a quantum computer, a special kind of quantum computer in that case, it is possible to use a quantum effect called tunneling. And what that allows for is just flying through all these hills and valleys. So no matter where you start, you just fly through and then you end up in your valleys. And that's where the remarkable power of these machines comes from. And I hope that gives a good overview of why it makes sense to use it.
Thank you so much, Florian, for that cool talk. I wish